It's another lesson from Professor Zema Ekpete on Group 13 metals of the periodic table. You are welcome, my viewers and my students. Thank you for always watching my videos. Don't fail to subscribe, like, comment, or share this video. Today we'll be looking at the Group 13 elements of the periodic table, and the objective of this lesson is as follows. To identify the elements in the Group 13 of the periodic table, to be able to write their electronic configurations, describe the periodic trends of the group, write the equation of the formation of their oxides, hydroxides, and halides, and also describe the oxidation states of the Group 13 elements. The boron family, as they are called, that is the Group 13 elements, starting with boron. The Group 13 elements are the first group in the P block of the periodic table. All the elements of Group 13 are also called the boron family. The periodic table is segregated into S, P, D, and F blocks. And we know that this segregation is done based on the valence electron. If the valence electron falls on the piece of shell, it comes in the big block, and so on. The members of the Group 13 elements are boron, aluminium, gallium, indium, and thallium. Boron has an atomic number 5, aluminium 13, gallium 21, indium 39, and thallium 57. The electronic configuration is in the S, NS2, and NP1 shell. Their valence electrons are found in the S subshell and also in the P subshell of the periodic table. Boron is found in 2s2, 2p1, aluminium 3s2, 3p1, gallium 4s2, 4p1, indium 5s2, 5p1, and thallium 6s2, 6p1. Aluminium in this group is amphoteric, meaning that the metal disintegrates in weakened mineral acids and in sodium hydroxide. So it is classified as amphoteric. How do they occur and how are they extracted? We find that boron is in limited quantities and is a product of subatomic particles created from radioactivity. And aluminum is not present in a free state, though it is the earth's most abundant metal. It's found in ores such as bauxite and cryolite. Gallium is found in trace amounts in the mineral diaspora, bauxite, sapphirite, germanite, and coal. And indium is a rare element that is only present in around 0.1 parts per million on Earth. Thallium found in ores of zinc, lead, or copper. It is also present in oxides, which is useful in the production of sulfuric acid. And nihonium is a synthetic element, that is, it does not occur in nature, but is present in laboratories. The electronic configuration or electronegativity and ionization energy of the members of this group. We find out that electronegativity decreases down the group, with boron being highly electronegative, followed by thallium, followed by indium, followed by gallium, and then the least electronegative is found to be aluminium. There are 3 electrons in the outermost shell of this group 13 elements. So these metals are characterized by 3 ionization energies. The first ionization energy of these elements are lower than the corresponding values of group 2 elements. However, the second and third ionization energies are much higher. This is because the first electrons to be lost by a group 13 element is a p electron. The p electrons are less penetrating than the s electrons. Therefore, lesser energy is required to remove a p electron. The second and the third electrons to be removed from an atom of any group 13 elements are from the s orbital. And we know that removal of s orbital, particularly from a positively charged ion, after the removal of a p electron, requires more energy Therefore, second and third ionization energies of group 13 elements are always very high. Their atomic radii, melting point, and boiling point. The atomic radii of these elements of this group increases down the group, with thallium having the highest atomic radii. But the atomic radii of gallium is lower than that of aluminium. This is because of the presence of the d orbitals in gallium. The d orbitals are highly diffused and offer a poor shielding effect. As a result, the nuclear charge increases, the radius decreases. Boron has the smallest atomic radii among the group 13 elements. Among the group 13 elements, boron has the highest boiling point, whereas gallium has the lowest melting point. And gallium is said to exist as a liquid in summers. Boron also has a smaller size, forming strong covalent bonds with other atoms. Therefore, the melting and boiling points of boron are highest among all the group 13 elements. Their oxidation state. Oxidation states of boron, boron does not form +3 oxidation state ion due to its high ionization energy. So it gives mainly covalent compounds. It is able to share with other elements in the periodic table, like elements in the halogens on the period. Boron can share with them, the halogens. Aluminium has a tendency to form aluminium 3+ ion in the solution due to its high hydration energy. And gallium, indium, and thallium show +1 and +3 oxidation state. The +1 state becomes more stable than +3 in going from gallium to thallium. The resistance, or as we go down the group, the tendency of s electron in the valence shell to take part in bonding decreases. This resistance of a pair of s electrons to be lost or to participate in covalent bond formation is known as what we call the inert pair effect. We all know that the p electrons in this group can be removed easily, but the s electrons cannot be removed easily. The inert pair effect becomes more operative towards the bottom of the group. Thus, for heavier elements of the group like gallium, indium, and thallium, the +1 state becomes more stable than the +3 state. Formation of the basic character of the hydroxides and their oxides. We'll find out that basic character increases down the group. Formation of boron hydroxide and boron oxide, they are acidic, and aluminum hydroxide and aluminum oxide are amphoteric. Gallium hydroxide and gallium oxide are also amphoteric. Indium hydroxide and indium oxide are basic, and thallium hydroxide and thallium oxide are strong base. So we say that basic character increases down the group. Reactivity of group 13 elements towards oxygen. The reactivity of group 13 elements towards oxygen increases down the group. Boron is unreactive towards oxygen, in its crystalline form, but if it is finely divided, it can react with oxygen on heating to form boron oxide. So all of the elements of group 13 react at high temperatures, forming their trioxides, M2O3. The oxides of the other elements can be prepared by the thermal decomposition of the hydroxide or their nitrates. If we decompose aluminum hydroxide, will form aluminum trioxide and 3 molecules of water. The reactivity of group 13 towards halogens. They react with halogens at high temperature to form trihalides. Like the example we have here, boron reacting with fluorine, it forms rhodium fluoride, and it can react with chlorine, it can react with bromine. That's their reaction. They are highly reactive at high temperatures to form the trihalides. Reactivity towards metals. Boron combines with metals to form borides, and it is only boron that combines with metals to form borides. The rest of the elements of this group are reluctant to combine with metals, and that shows the non-metallic character of a boron. Boron reacts with magnesium to form magnesium borides. Reactivity towards water. Boron does not react with water or steam. However, at very high temperature, it can react with steam to form the boron oxide, and hydrogen gas will be released. Aluminium does not appear to react with water because an outer layer of aluminium oxide solid forms and protects the rest of the metal. Bond formation. We know that to achieve a noble gas structure in the formation of ionic bonding, transfer of electrons from one atom to another is required. It is also possible for atoms to react or reach their stable structure by sharing electrons to give covalent bonds. A boron family atom has 3 electrons in its outermost shell, and there is no possibility of it reaching a noble gas structure by simply sharing of electrons. Is this a problem? No. Boron has formed the maximum number of bonds that it can, and this is a perfect structure. Looking at the structure it has formed, a structure called boron trifluoride, that is the compound it formed, by sharing electron with fluorine. Each fluorine atom starts with 7 valence electrons and uses only one of them to bond with boron, leaving it with 3 lone pairs to complete its octet. In contrast, the boron atom has no lone pairs as it uses all its electrons. Boron trifluoride is referred to as an electron deficient compound because the boron atom does not have a full octet, but on 6 electrons are its 3 single bonds, making it a Lewis acid. What are the uses of this boron family? Boron is commonly used in fiberglass and is used in making of pots and plates and vases because it is an insulating material. Aluminium, we all know, is used in construction material, construction work, electrical gadgets. We use it in also roofing our homes. It's good for aircraft bodies and bicycle components. Gallium arsenide is a part of semiconductor that enhances, it's an enhancer and is good for solar cells. Gallium is used also in LED lighting. Indium is good for electrophoretic displays, is good for road lights, solar panels. It's also good in plasma display boards and electrochemical displays, also used for sodium light, etc. So the compounds of this group are highly, very, very useful compounds, useful elements. The study question. What is the oxidizing property of the group 13 elements? Which element of group 13 is a strong reducing agent? Explain the basic character of the oxides of this group. So far, we have come to the end of this lesson. I wish to ask you to subscribe, like, comment, and share. And I thank you for patiently listening to this lecture or this lesson to the end. See you in the next class.